On this F150 with the 2.7 EcoBoost, P0175 generally means the engine computer may be seeing one cylinder bank running richer than expected. The truck may have a check engine light, rough running, a fuel smell, poor fuel economy, or it may seem pretty normal. Keep the fault areas broad at the start. Fuel control, air metering, exhaust feedback, intake or vacuum issues, wiring and connector condition, and basic engine operating conditions can all be involved. So don't jump straight to a part. Start clean, prove the concern, and follow a structured diagnostic approach. Before getting deep into P0175, look for anything obvious that matches the customer's complaint. Check available OASIS or TSB information if available, and check repair history, especially any recent work that may not have been completed correctly. Then make sure the battery and charging system are healthy, and verify battery SOC is greater than 70% before diagnostics begin. Scan all modules for codes that may help decide where to start. If other codes are present, check what they mean first. Circuit faults come before system or performance faults, and if several circuit faults are present, look for a shared power, ground, splice, or routing issue before chasing individual components. Also remember, the concern needs to be present during testing. If it is not present, don't use that test session as a reason to replace modules or components. Next, work through the vehicle basics. Inspect wiring harnesses for damage, chafing, and correct routing. Check fuses, circuits, connectors, and component connections. Look over the vacuum lines and air intake for leaks, restrictions, and routing problems. Inspect hoses for damage, leaks, blockage, and routing. Check fuel quality, including octane, contamination, and seasonal blend. Inspect the fuel tank and fuel lines for damage, leaks, and routing. Confirm coolant level and quality with the engine operating at correct temperature. Check oil level and quality, and inspect the exhaust system for damage, restrictions, and routing. For a rich code concern, these basic checks matter because they can keep you from blaming data before the vehicle itself has been checked. When you connect test equipment or jumpers at connector pins, use the correct flex probes, such as Rotunda flex probes, NUD 105 R025F, or terminal probe kit 418-S035, so you don't create terminal damage while diagnosing the code. Check male to female terminal fit with the mating pin. Very low separation force means the pin is damaged. If the connector shell, guide, or retainer adds drag while checking small terminals, remove the pin as needed to check the fit correctly. Damaged connectors, pins, or terminals are to be replaced. Then use the scan tool to read PID inputs, output states, and diagnostic states, and monitor PIDs in the data logger. Command outputs only when that function is available. Before condemning a module, understand how the system is supposed to work. Make sure programmable parameters are set correctly, and keep the active DTC diagnosis first before moving on to the rest of the system checks. Then test hardwired and networked inputs, test outputs, and check for module software updates. If output state control shows the module can operate and output normally, shift your attention back to the inputs instead of blaming the module. Also, don't power or ground module-controlled components directly with jumper wires unless a test specifically calls for it. For electrical checks, don't rely on unloaded voltage alone. On a power-providing circuit, measuring voltage with the load disconnected may only show an open circuit. It may not show excessive resistance. For circuits carrying approximately 200 to 1000 mAs, load the circuit with a 250 to 350 mA test light and measure voltage with a DMM while the test light is connected. If voltage drops under that load, suspect excessive resistance. Conductor sizes 24 gauge, 0.5 millimeters, or smaller are generally used to carry approximately 1000 mAs, 1 ampere or less. For circuits carrying more than 1 ampere, use a load that draws similar current, like a brake light bulb. Conductor sizes 20 gauge, 0.8 millimeters or larger are generally used to carry 1 ampere, 1000 mAs or more. Higher current circuits should be checked with voltage drop. For ground-providing circuits, measure voltage drop while the component is operating or attempting to operate. Use an ohm meter accurately only with the battery disconnected, because voltage in the circuit can corrupt the reading. For most small diameter, 18 gauge and smaller wires, expect less than 2 ohms, and for most harness circuits, expect less than 2 ohms. A standard DMM ohm meter's low resistance resolution, approximately 0.1 ohm, limits its accurate use to circuits carrying less than approximately 5 amperes. Reverse the DMM leads. The resistance should not change unless a semiconductor is in the circuit. If the reading changes when the leads are swapped, treat that result as invalid. For unintended continuity to ground or to another unpowered circuit, disconnect both ends and expect greater than 10,000 ohms. For unintended continuity to a powered circuit, disconnect both ends, turn on ignition, run power, and expect no voltage. Backprobing has its place, but use it only when the circuit has to be tested under actual operating conditions, or when a voltage drop test requires it. Every voltage drop test should show a small amount of voltage. Expect less than 5% of circuit operating voltage. The 0-volt result usually means the test conditions are wrong, there is no current flow, or the back probe connection is poor. Do not force probes into connectors. Use back probes designed for the job. Do not use back probing as the only test for voltage presence, and do not use it for continuity or open circuit checks with an ohm meter between 2 points. Disconnect and isolate the circuit for those tests. When jumper wires are needed, always use fused jumper wires. The recommended universal testing jumper wire fuse is 5 amperes or less, unless the load requires a larger fuse. Use flex probes to prevent terminal damage, but do not use them to power cooling fans, blower motors, or other high current devices. Flex probes are not intended to carry high current greater than 5 amperes. Follow the jumper wire directions carefully, and never fix a circuit by overlaying a new wire in parallel with the old one until you understand why the original circuit failed. When you make a voltage drop measurement, connect the voltmeter at the beginning and end of the suspect circuit. The circuit has to be operating, or at least attempting to operate, with power available to flow. Follow conventional current flow with your meter lead polarity. A 0-volt voltage drop reading points to bad meter connections or a component that is not turned on. A small voltage drop is normal circuit loss. In 12-volt circuits, that is usually less than 0.5 volts, and the general expectation is less than 5% of circuit operating voltage. Voltage greater than 0.5 volts indicates abnormal voltage loss, which points toward high resistance in wiring or connectors. For a voltage in, voltage out check, put the negative meter lead on ground or battery negative, and measure the power side and ground side of the load with the circuit operating. The power side should be within 0.5 volts of battery voltage. The ground side should be greater than 0 volts, but less than 0.5 volts. A reading of 0 volts, or source voltage, indicates an open circuit. Keep verification separate from testing. Once testing has proven and corrected the actual fault, put the vehicle back into the same type of operating situation that showed the concern. Verify the repair, and confirm P0175 stays gone. The takeaway is simple. For P0175, don't guess rich condition parts. Start with the basics. Confirm the concern is present. Check related codes in priority order. Protect the terminals, load the circuits, and prove the fault before replacing anything. For more diagnostic training, visit stepdiagnostics.com.